Welcome to the MOOC course on operating systems, and today's topic is inter-process communication techniques. So, we all know that operating system consists of so many processes, and all these processes need to cooperate each other to accomplish the tasks which are highly complex. So, modern operating systems need many processes to run simultaneously. So, we need to provide an environment where these processes will interact with each other and they can share common resources, and these resources has to be accessed mutually exclusively to each process. In order to provide such mechanisms, we use inter-process communication techniques. The topics for today's IPC technique consists of objectives of IPC, need for IPC, types of IPC mechanisms, includes message passing and shared memory, and we have to provide synchronization during accessing the shared resources. Further, we have synchronization IPC, then IPC in distributed systems, common IPC mechanisms, and IPC in Unix and Linux environments, and at last we discuss about the advantages and disadvantages of IPC. So, in modern operating systems, multiple operations run parallelly. So, these operations will need to access a common resource. So, if you want to access the common resource, we have to provide mechanisms that can make sure that these resources are accessed by one process at a time. So, this process will exchange data and they coordinate among each other. So, for this purpose we need so many techniques, and the first basic technique is the IPC, inter-process communication technique, which is very much vital for parallel processing of data in the modern operating systems. Then client server systems, where the client will be in one place and server will be in another place in the network, and these two machines are connected via network, and still process running in client and server can communicate with each other. And we have the multi-threaded and distributed applications where lightweight processing can also be enabled by providing the appropriate sources and synchronization mechanisms. So, if you look at the IPC in terms of definition, so it allows the independent processes to communicate with each other and to synchronize and share data. So, we have to provide a communication mechanism, we have to provide synchronization mechanism to ensure the mutually exclusive access of data, and at the same time we have to share the data among multiple processes. So, this is the ultimate purpose of going for IPC technique. So, this IPC technique can be implemented using within a single system, or it can be used among two systems which are connected in the network. So, this may be geographically apart, but still the process can communicate with each other. It can send data from a client machine or a machine which is located in one place to another machine which is located in some other place. So, this is the basic fundamental for multi-programming and real-time systems. These real-time systems are very much in need of process to cooperate each other extensively. So, we have to provide IPC mechanisms for such cases. So, the main objective of IPC is it enables data sharing between processes, and it provides the synchronization mechanism, which is mainly essential for accessing the data exclusively meant for the particular process at the particular instant of time. And we have mechanisms that can provide communication between local and remote processes, and we have modularity in separating functionalities into different processes. So, we have different advantage of having inter-process communication among multiple processes, and also we have the limited resources like memory and files, on these resources can be shared between processes. So, this is the main objectives of IPC. The need for IPC is processes in the OS are isolated for protection and stability. So, we should not cross the boundary of one process access to among other processes. So, it is also very much essential. So, IPC has a stringent mechanism that ensures that only the particular process accessing data, and it is not breaching the rule of accessing the data which is not supposed to be accessed at that particular instant of time. So, many applications in modern operating systems need huge interaction between among the processes, and there are few examples like web browser process, that is sharing tabs and cache. This is highly interactive, and we have the database and client server communication, where the database and the server communication is quite often, and we have to ensure that this access is legitimate and appropriate. And we have an example in Linux called pipeline in Linux. Overall, the IPC is going to provide an efficient and controlled communication. So, the basic types of IPC mechanisms are message passing and shared memory. So, what is message passing is it is just data is transferred via the kernel managed messages. There is no need for shared memory in between. It directly sends message from one process to another process. In that case, synchronization is not an issue, because the sender and receiver are alive, and these two can exchange messages indefinitely. So, the one basic challenge is the sender and receiver have to send fixed size messages between the two. The second one is shared memory. So, here the portion of the memory is shared by the two processes, and this sharing is enabled by giving access to the content, but at the same time we have to ensure that one process accessing the data while the other process is waiting for its access. It has to wait for its turn to get the right for accessing the data. So, for that we provide synchronization tools to avoid this conflict. So, it provides the mutual exclusive access for the shared data. So, this is the diagram shows that the message queue is between two processes. We have a queue which is having fixed size blocks of data that is sent from one process to another process. In shared memory, the memory is shared between two processes, process A and process B, and we have mechanisms that ensures that this shared data is accessed exclusively by process at whenever they need. The next is the message passing concept. Here we have processes communicate by exchanging messages through OS. The kernel acts as an intermediary for sending and receiving data. This is best suited for small data and distributed systems. For example, the sender will send data by placing the destination and the actual content wants to transfer, and the receiver will specify from where it has to receive and what is the message. So, this is the direct communication between the sender and receiver. It is mainly used in microkernel architectures and client server models. So, we use send and receive mechanism. So, it sends data and it receives data. So, if you look at the code, you can see here we are going to create a child process. So, hope you all know that for creating a child process in the operating system, we use a fork system call. So, if you use fork system call, a child process will be created and the fork will return two values. One is 0 and another is a non-zero value. So, the 0 is assigned to the child and the non-zero value is nothing but the child process ID which is assigned to the parent. If you look at the code, this statement is fork is equal to 0, it means it is child. So, the message sent is received by the child. So, print child as received, else if the FD is 1, then the message is printed. So, we use fork system for creating child process, and we use message passing concept inside that between parent and child. So, the basic characteristics of message passing are, there are few ways we can exchange messages using message passing IPC technique. The first is direct communication. So, in the direct communication you have to explicitly specify the process which is going to transfer data and which is going to receive data. The name of the process explicitly mentioned. In indirect communication, there is no explicit mentioning about the process, but we use in between a concept called mailboxes or ports that will have data, and from there we can access. So, one process will put data in the mailbox and another process can access from that. The next is synchronous communication. So, here the sender waits until the message is received by the receiver. This is synchronous. So, it both will have mutual understanding that I will send only if you receive, and I will send the next message only after receiving the previous message. The asynchronous communication, the sender continues its transmission without waiting for the receiver to receive. So, it keeps on sending and the receiver will receive later. So, the sender will keep sending automatically. The next is the automatic or explicit buffering. So, here we use buffer in between and we store the data in the buffer and later the data will be retrieved. So, these are the various ways we can implement message passing techniques. So, if you look at in detail about direct and indirect communication, in direct communication addressing is implemented by explicitly mentioning the process name, whereas in indirect communication it uses in between the mailbox as we discussed already. And the next is the flexibility. Yes, in direct communication it is very tightly coupled because we have to exclusively specify the process name, we cannot change, but whereas in indirect communication it is loosely coupled where we can put data and later we can access by any process. Example, send P1 comma message. P1 refers to the process and the message is the actual message you want to send, whereas here in indirect communication send mailbox comma message. So, you are not explicitly saying this process is transmitting data, you can put that in the mailbox and the message can be retrieved. And where we can use the use case here is fixed process pairs. So, if you want to have message passing between two defined process, we can use this direct communication method, whereas in indirect communication method we can have dynamic communication setup where we can access data which is stored in the mailbox by any process. So, this is the main direct and indirect communication which has its own plus and minus. And the second category is synchronous versus asynchronous communication. In synchronous, the sender waits for the acknowledgement before continuing its transmission. Example is remote procedure call, we will discuss that shortly. And asynchronous is sender proceeds without waiting for the reply. So, sender keeps on sending the data without bothering about whether the receiver is receiving or not. Example is message queues generally keeps on sending data, and UDP sockets. So, it is user datagram protocol networks where we use this is for unreliable communication, where the sender will not bother about the receiver whether the receiver is receiving or not. Of course, we have to pay for that. Synchronous is reliability, but very slower because we have to ensure that the receiver is receiving the data. It takes time to check and transmit the next data. Asynchronous efficiency, but less control. So, you can send any amount of data, but we cannot have a control over the transmission and reception. This is a trade-off between this. The next is buffering and queuing, where we have intermediate temporary buffer to store the data, and from that buffer we can retrieve the data. So, messages are stored in buffers temporarily. The buffer size can be of various values. One is zero capacity, where there is no buffer at all. Sender must wait. Bounded capacity is limited queue. Sender waits if full. So, you can put data in the buffer for some time, and if the buffer is full, it has to wait for the buffer get empty. Unbounded capacity is infinite queue. Here, ideally, it is not possible to have unbounded capacity of buffer. So, it keeps producing, it keeps sending data, and assume that the buffer is unlimited. So, we can retrieve data in the later point. So, all these three will have its own value of throughput, latency and synchronization. Design mechanisms are different for these three. If you look at this diagram, we have buffer creation, how buffering works, data storing in buffer, then we have to manage the buffer, whether the buffer is zero capacity or bounded or unbounded, then data is processed and relieved, and buffer flushed. So, we have to clear the buffer. So, the message queue is the process sends the data to the message passing module, and the message module will pass this data to the receiving process. Shared memory is the another technique. Here we use the region of physical memory is shared among the process. So, we have a portion of memory dedicated for using this shared data. So, this will be shared by many processes. So, we basically do read and write operations over any memory location. So, if you allocate a shared memory, we perform read or write. So, you can give access permissions for either to read or write or to perform both. Offers faster communication than message passing. So, message passing needs to establish a queue, then it has to implement direct or indirect or asynchronous way, whereas in shared memory the memory is allocated, and only you have to check is which process allowed to access the shared memory. So, it is faster, but we have to provide a synchronization mechanism. So, it requires synchronization tools to prevent conflicts among the processes that are trying to access the data. If the data is too sensitive and if it is it keeps updating itself, then we have to be very careful that which process is going to update and which process is going to access after updation. So, this synchronization is the major thing which has to be implemented in shared memory especially. The basic problem which we can talk about this issue is producer and consumer problem, where the producer keeps producing the items and consumer keeps consuming. So, we have to ensure that producer is not filling the buffer and buffering getting overflow, or the consumer is trying to access an empty buffer. So, if you look at this program, we use the shared memory. So, F2K is the function which creates the key. So, SHM file is the path of the file which you want to access, and this is the ID, process ID. Using this shared memory get function will create a new shared memory. So, the key is generated using F2K, that key is used here, and the length of the message is represented here in the second argument, and the third is the 0666/IPC create is 0 represents the octal representation, and this 6 represents the access rights, and IPC create is it indicates that if there is no shared memory created, it will create a new shared memory, and this shared memory can be used for accessing by the process. Here we have the shared memory attach, which uses the same ID created at the previous function shared memory get, and this ID is used, and the null pointer is if you put null, the OS will use the address by itself, and this is for flag. So, this flag says that you can perform read and write operations over the shared memory. It gives full access. If it is 1, you have to specify whether it is read or write. So, here we use a fork system call again to create a child process. Inside the child is reading the data, and once the child reads the data, you have to detach the shared memory, otherwise the next is the parent process. So, both processes will detach from the shared memory access, and at last we have to remove the shared memory from the system to release the resources which is occupied. So, if you want to see the example producer consumer problem, so scenario is producer writes data into the buffer and consumer reads data from the buffer. The challenge is avoid overwriting unread data. So, if buffer is getting filled by data or by the producer, so we have to ensure that it is not filling buffer before consuming by the consumer. So, at the same time we have to check whether it is avoiding reading the empty buffer. So, if it is buffer is empty, there is no point in reading. So, we have to check both conditions, both extreme cases. So, for that we use mutex, mutual exclusion options. So, here we have the p thread. P thread is a POSIX thread, which is a lightweight process which ensures that the producer is producing data and he is writing the data in the buffer and he is not overwriting before reading the data by the consumer. Once it is produced and placed in the buffer, then we can call the unlock mechanism, that is p thread underscore mutex underscore unlock, and we release this buffer. Thereby the consumer can enter into the buffer and it can consume the data. Once it consumes the data, it can unlock. So, producer is producing and consumer is consuming by passing this criteria. This is the synchronization mechanism which we implement. Basically, we use semaphores. So, to accomplish the overall task of message passing and synchronization, we use shared memory which contains the message plus the semaphores for providing the synchronization between the producer and the consumer. So, likewise we have a lot of techniques for providing synchronization that we discuss exclusively in the synchronization topic. In a shared memory systems, how IPC works. So, in shared memory systems we call functions like SHM get in Linux. Once it is created, process attach the same memory region to another process. Communication is through only the shared variables, and synchronization is handled using semaphores or mutex as we discussed, and it is highly efficient in real time and multimedia applications where the interactions among the process will be huge and most of the process will be sharing or accessing the same data. At the same time, we have to ensure that this data is accessed mutually exclusive by each process. So, this diagram shows that. So, we have process A and process B, both are accessing the shared memory. This access is controlled by synchronization techniques. Now, if you want to look at the various synchronization mechanisms in IPC that can provide mutual exclusive access. So, we have few, and before that we see what the synchronization mechanism does in IPC. It ensures orderly access to shared resources, prevents race conditions and inconsistent states. So, race condition is more than one trying to access the same, and it leads to different states of the process. Common mechanisms like semaphore. So, semaphores uses integer concept to ensure the controlled access or mutual exclusive access for shared content. And next is mutex locks. It is like lock mechanism. So, once you enter, you lock it. Once you come out, you unlock it. There be others can lock it and they can use and they will come out and they will do unlock. The next is monitors. These are all high level concepts with conditional variables. Checking conditions, we can ensure that the shared variable is accessed mutually exclusive by the process. And if you go in deeper and fine grained controls like using techniques like spin locks, this mainly used in threading concepts in executing processes that we discuss in separate topic exclusively. It comes under threads and synchronization mechanisms. The next is IPC in distributed systems, where the systems are not located in the same place, they are located in different places. So, it involves communication between processes on different machines, and these IPCs will be implemented in different ways. One is remote procedure call method, this is old method, and the second is by using sockets, either reliable or unreliable sockets as per the convenience. The next is the message queues in distributed operating systems. So, these are all methods that can be used for communicating between two processes that are running in two different machines, and these machines are located geographically apart. So, we have to handle certain issues in this situation like latency, network failure, and how to address the other machine. So, I hope you all know that how to access another process running in another machine. So, we use IP address, we use port number, all these concepts will be used appropriately for contacting two different processes running in two different machines. Okay. So, the best example is client request service and server response via a socket. So, look at this example, we have machines connected with different switches or different locations, and all these are communicating with each other. So, it is not about within a single system, this machine is communicating via this, and similarly other machines can also communicate. So, we have to give proper addressing mechanisms, we have to provide we have to address the network latency in communication, and in case of link failure or any device failure, we have to address that also. So, distributed systems process communication is much more complex than communication between processes within the system. So, the first technique which is about a remote procedure call, we call it as RPC. So, it is an abstraction of a local procedure call between process on a network system. It is responsible for creating a request from a remote system to another system, and this system will respond with an answer. That is why it is called remote procedure. It is invoking a procedure in the remote machine. So, we call stubs in the client machine for actual procedure existing on the server. So, here we generate a request, and this request will be formulated in the client machine, and this by using some format we call it as marshalling, and this will be sent as a request to the server, and server will execute the procedure and it will return the value, and server will first demarshal the values and it will execute the procedure. It sends back to this client by using the same procedure, that is marshalling and demarshalling. It happens both at this client to the server and server to the client. So, the client side stub locates the server and marshals the parameters. Marshals is the required parameters that are to be added along with the request data to reach the destination. So, we add extra data format mechanisms that can take this to the receiver intact. Okay. The server side stub or skeleton receives this message, unpacks the marshaled parameters and performs the procedure on the server. It do the execution at the server, it return back by again doing marshalling, and the client will do unmarshalling and it will take the value. So, that is what is mentioned here. Vice versa happens on the opposite direction from the server to the client. So, if you look at in detail, this diagram shows that we have the client application. So, the local application or operating system is accessing the client application running in the local machine, and it is having the local stub, and it uses the RPC mechanism which do the marshalling, and it sends the remote procedure call request, and again the RPC mechanism in the server side, it will run the remote server application, and this procedure call is executed and it will get the result as a local response, and this local response will be accepted by the local stub in the server. It marshals the data and again sends back to the client. Again client will demarshal and it will give the response back. This response will go to the client application, this will be processed. So, this is the typical RPC mechanism structure. The next one is sockets. So, this is mostly dealt in network programming, where there are different perspectives of looking at sockets, but here we look, the socket is just an abstraction to communicate between two processes. So, it is like an entry and exit point for data. So, each process opens the socket and pair of sockets can be connected. So, what we have to do is the sending machine and receiving machine will have to create a socket, and this socket has to be calling so many system calls for performing its actions. So, these are the system calls the socket has to be executed. So, first is create the socket. As I said, socket is an abstraction that acts as an entry and exit point for data. This socket has to be bind with the IP address and port number. We have to give name for the socket. We have to say that the socket is pertain for doing this particular job. So, it has a IP address and port number as the value. And next is the listen socket, which is normally in the server side. So, these socket system calls mentioned in this slide is about socket system calls which are to be executed at the client as well as in the server side. So, the client side we have to execute socket, then connect, send, receive, and of course close. Whereas in server side we have socket, bind, listen, accept, send and receive, then close, no connect in the server side. I am talking about TCP, that is reliable socket communication between two processes running in different machines. So, in detail if you want to study about sockets, it is a big course. We have network programming as a separate course, but here I will just give you a glimpse about how sockets will be used for communication. If you look at this diagram, we have a process P1 which is having a socket that is created using the socket system call, which has returned a value called FD, that is the file descriptor. Socket will return a value that is similar to files in the Unix operating system. So, Unix everything will be treated as files. This will be given a file descriptor if the file exists. So, here also we have a file descriptor, we call it as socket descriptor in particular, and use that descriptor and send a message using send message and you can receive. Similarly, the computer B which is having process P2, that also will create a socket and it receives the socket and it sends and receive. For both sides it can send and receive. One process writes a message in one socket and another process will read it, and the same thing happens in the other side also. So, it is a bidirectional communication. So, this process can be in the same machine or different machines, but still we can use this sockets. If the processes are running in different machines, basically sockets are used for that. If it is running in different machines, then we can use network in between the two machines for communication between these two processes. So, if you look at the types, we have different types of sockets. We call Unix domain, we call it as local socket, used to communicate in process on the same machine. So, if you want to have communication among processes in the same machine, we use Unix domain, and we have internet sockets are used to communicate in process in different machines. We have to mention the path name, IP address and port number to identify the sockets, as I mentioned. The bind system call is meant for that. And we have the client server paradigm, where one process opens a socket first and another process connects to the socket to the first one. So, basically the server socket will be always running, whereas the client, you can create a socket, you can communicate with the server socket and you can exit. Thereby the other clients can create their socket and communicate with the server. So, that is the basic difference between the client and server. And we have two basic classes of sockets. One is connection based socket and connectionless socket. So, this is the connection based socket, where there is a explicit connection between the two sockets, and connectionless socket is it can send and receive data. So, multiple sockets can send data to a same socket, whereas in connection based socket, the connection will be established between two individual sockets. So, this socket can communicate only with this socket. If we close this, the connection will be terminated, whereas in connectionless, the receiver socket will be open, and any sender can keep sending the data to these sockets. So, we can call the second one as UDP sockets and the first one connection based socket as TCP sockets. So, system call for creating a socket is it takes some arguments. These arguments will intact generate a descriptor, we call it a socket descriptor. All the other system calls will use this socket descriptor for their own job. For example, binding, listening, accept, all these will use the socket descriptor. If the socket is successfully created, then only all other system calls will be active. So, by default a socket is bind an address, and using the bind system call, as I already said, the server socket bind to a well known address so that the clients can connect. So, always the server socket should be running in a well defined port, and the service should be known to every user, I mean all other processes. Thereby these processes can connect to the server for a well defined task to be accomplished. So, the server sockets are binded with a well known address, whereas the client sockets need not to be bind. The OS can assign temporary address, because the client can join for communication, it can go out, whereas the server should be always listening for client requests. So, that is why the server should be always bind with a well known address. So, once it is done, the close system call is used for closing the socket once it is done. So, this is the overall overview about how sockets can be used for communicating between two processes running in two different machines. And we have the common IPC mechanisms like pipes, named pipes, message queues and shared memory. So, the pipes is a unidirectional channel between related processes. So, here there should be an ancestral relationship between the processes which are interacting, like parent and child. So, you can use pipes for that. So, it can send in one end and it can receive in another end. Similarly, we use named pipes. This is for communication happening between unrelated processes, not necessarily that there should be an ancestral relationship like parent and child. It can be two different processes. It can use named pipes. We already discussed about message queues and shared memory. So, it is the kernel will initiate the sending of messages. It can be used in these use cases like job scheduling for message queues and shared memory, where we have common memory region, as we already seen, between two processes or many processes, and this is for fast local data sharing. So, if the data is common, everybody can share the data very easily. Otherwise, we have to give exclusive data that may not be appropriate for all the cases. We cannot have distinct data for each process. One data should be shared by many processes at most of the times. That is why we are going for these techniques. So, if you see Unix and Linux operating systems in particular, the IPC techniques can be implemented using various system calls, which has its own definitions like pipe, MK54, there is named pipe, then message get, shared memory get, socket. These are all system calls used in Linux and Unix systems. And we have commands like IPCS that displays the various IPC resources used in the system. And if you want to remove those resources, we can use IPC RM, that is remove. And we have, as is mentioned, the examples of shared memory is semget and semattach. This is for creating the shared memory, and it is for attaching the shared memory between any process that wants to share it. Then message queue, where it is used for sending and receiving. If you look at this diagram, it has the pictorial representation of how all these IPC techniques can be implemented. The first is pipe. Here we can see the one end writing and another is reading. The second is message queue, one process writing in the queue, and all these sizes are fixed, and the message will be received in the process B. The third is about another way of communicating between processes called signaling. As we all know that if you press a keyboard like Ctrl+C, it generates a particular signal, and it is meant for a specific purpose. So, it generates a signal and this signal will be sent to another process that will have the signal handler that will execute the function and it will give a result. So, if you create any signal, the signal will have definite purpose and it calls the respective signal handler function and it will give the response. So, likewise we have this mechanism. The next is the semaphore. So, we already discussed, which is an integer variable which plays a major role in giving permission to access a value in the shared memory. So, we have acquire and release. Acquire is acquiring the right to access the data and releasing is as I am finished and I am going to release the resource, thereby another process can access. So, this is how these techniques are used, and we have the shared memory which we already discussed, where shared memory is common between process and they can mutually access this shared memory content. So, the advantages and disadvantages of IPC, if you look at main advantages, it enables cooperation among the process and enhance the performance of the overall system, and it promotes the modular system design. So, as we have the scope for having modularity in this implementation, since one is accessing the data or sending the data and another is receiving, not doing simultaneously. So, we can have respective system calls and all this will be invoked as and when necessary, and of course, it improves the overall performance by exhibiting the parallelism, and it facilitates client server and real time communication. Yes, using IPC we can have communication among systems which are geographically apart, and real timely we can do that because we have a lot of process running simultaneously. All this process will be interacting and it needs quick response. So, mechanisms will provide that. Of course, anything will have advantage and disadvantage. If you look at the disadvantage point of view, it increases complexity in synchronization. So, if you have multiple processes involved, we have to ensure that all these processes are mutually accessing the content without any conflict. So, in order to implement that, we need to implement synchronization mechanisms very carefully, otherwise it ends up with accessing the wrong data. And another issue is risks of deadlocks, race conditions, security issues if it is not properly implemented, because many are sharing a particular resource. Definitely there is a chance for all this problem. Both can attempt at the same time, both can breach some rules of accessing the data. So, anything can happen. So, implementing synchronization mechanisms is a big challenge. We have a lot of overheads in kernel calls during message passing. So, a lot of calls has to be invoked for sending and receiving messages. So, these are the advantages and disadvantages of IPC. So, overall IPC is the core concept in operating system that enables process communication and coordination among processes, and the two main approaches used for IPC is message passing and shared memory. So, we have discussed exclusively about how message passing is done and how shared memory is accessed by two processes without any conflict using synchronization mechanisms, and the synchronization mechanisms will ensure whether the data is accessed by the correct process at the right time, and in the meantime no other process accessing the data. So, it ensures reliability and data integrity, and it supports hugely in modern operating systems from OS kernels to distributed systems. So, IPC is the main mechanism that enables different processes are communicating among each other in a cooperative way to build high end complex systems that is mostly used by all organizations. So, overall I can say the effective communication between processes will lead to an effective operating system. So, with this I am going to conclude this IPC technique presentation, and I thank all the audience for patiently listening this lecture, and we see you in the next lecture in the operating system course. Thank you.